Welcome back, Precalcsters. I'm sorry that I'm not with you today. Zeke is not feeling well, and that's just part of, being a parent. So, welcome back. Today in class, despite me not being there with you, you're going to have the wonderful opportunity of working through a few more of these exponential and log equations. So, just to start us off, what I want to really focus on is we have these properties that we have listed, and we began solving some basic exponentials the other day. Remember that we use logs as a way to solve equations that otherwise we wouldn't be able to get great answers with. So for example, if we look at example C from the other day, to undo a 2 to the x, which in my mind, we're just thinking how do we get the x out of the exponent, we simply take the log of each side. As long as you remember to treat the log of whatever as a number like it is, we'll always be able to solve these things pretty straightforward. So, today's lesson, we're just going to expand on those ideas just a little bit, and we'll check out a couple of things here. Now, one of the types of problems that we'll see within our exponentials that can be kind of tricky are going to be quadratic type exponentials. So we'll jump in today right away. We're still in section 3.4. We're just doing the second half of it. So we're just going to add an example here then. And we are looking at quadratic type exponentials. Now, I've made the comment before, and I'm sure I'll make it again. Factoring is such a fundamental part of solving mathematics at this level that we may need to do a little bit of review and stuff. And by we, I certainly mean you may need to do a little bit of review and stuff with my assistance if needed. But let's just dig in. I'm going to work through one here on the video, and then with your classmates, your neighbors, whomever, I want you to work through a different one. And we're going to see that, hey, these look kind of like stuff we've done before. So, hypothetically, let's say that we are solving e to the power of 2x minus 3e to the power of x plus 2, and I want to know when is this equal to 0. Now, as we look through things, an easy piece to get goofed up on is that this looks so much harder, but it's really no different than things that we've seen. So annotating like crazy. My first thought is this looks awful. However, if we rewrite this expression, rewrite conveniently, we're going to see that, hey, even though this looks awful, we can solve problems like this. Specifically, what I want us to imagine doing is if I think of e to the 2x, I can rewrite this. Specifically, I think I can make this e to the x squared, because these exponents will wind up multiplying, and it's still e to the 2x, minus 3 e to the x plus 2 is equal to 0. And it might not feel like I've really done anything here, and you're not completely wrong. We are rewriting this in an equivalent form just to try to make a little bit of sense of it. I'm now going to use a little bit of convenient notation that normally when I write these, I do not write this down. However, it's helpful, especially the first time you're seeing these. Just for a moment, here's what I would suggest we do. If we let some u value equal e to the x, and all this is a placeholder, but if we do this, we get the following. And let's just check. Instead of e to the x, we would have u, and I'll switch to blue here. We would have in these parentheses, it would be a u, and I'm not even going to write them. So there's e to the x squared minus 3 e to the x plus 2 still equal to 0. By taking advantage of this little rewriting, all of a sudden our regular factoring stuff just shows up as normal. As a quick reminder, this is our factoring list. So GCF, binomial, trinomial, and then all of these things. As I look at this blue expression, the last one that I've written, I notice that there is no greatest common factor. It's not a binomial. It is a trinomial, and instead of being in x like it normally is, x squared plus whatever, we just simply have it as u right now. I notice that there is a 1u squared minus 3u plus 2, meaning we can just go through with normal factoring. I'm looking for factors of positive 2 that add up to a negative 3. Pretty sure it's negative 2 and negative 1. And then finally, because we have our shortcut with a leading coefficient of 1 right here, we can simply factor this immediately. We get u minus 2 times u minus 1 is then equal to 0. It is so common for the mistake to happen here where somebody looks at this and they solve for u and say, hey, check it out. U is equal to 2 from this first factor, or u is equal to 1 from the second factor. But remember, that u that we've written is just a convenient placeholder, which means now substituting back in, so plug or replace, I don't know why I start with an L. Let's go ahead and put u equals e to the x back in. Now, when we do this, it means that we now have an expression that reads e to the x minus 2 times e to the x minus 1, and that's all equal to 0. And we're just using this substitution. In solving this, remember, two factors, and let's check it out. My first factor, if e to the x minus 2 is equal to 0, what this would become would be e to the x equals a positive 2 when we add it to both sides. I will then take the natural log of both sides of this. On the left side, I see that there's a power property just waiting, and we get x times the natural log of e equals the natural log of 2. And just a little bit of definition and reminder, natural log is just log base e. This term just goes to 1, which means we get down to our final answer that x is exactly equal to the natural log of 2. There's one of our answers. For the other one, and I'm going to use this dark green color, if we set this factor equal to 0, we're going to wind up with e to the x minus 1 equals 0, which I'll add 1 to each side. We get e to the x equals 1. I'll take the natural log of each side, and on the left I've already used the power property. So ln of e to the x, and I move the x out front. This natural log of e here, once again, just goes to 1, equals the natural log of 1. And if you want to stop here, you can, but remember, e to the 0 is what equals 1 as our argument, which means we get x equals 0 as our second solution. And we have two separate solutions. We can check them, we can verify that they're good. This problem is essentially just a reworking of all the factoring stuff that we've already spent a huge amount of time on. All that's different is we have to use the natural log at the very end. So here's one example that we went through, or that I've gone through. What I want you to do with your neighbors, independently, however you see fit, I want you to work through the following. And here we go. We have e to the 2x minus 7e to the x plus 12 is equal to 0. And I want you to go ahead and get this written down, pause the video, and you will see a detailed solution, not a talk through, but I'll just show you the work that I have with the annotations. A detailed solution in 5, 4, 3, 2, 1. And here is my detailed work. So very similar process. We rewrite this so that it looks like we have something squared minus something, or number times something in this first line up here. Then we use this clever substitution of u equals e to the x. We rewrite it, factor with that leading coefficient of 1. Just a reminder, this sign, the 3 dots right here, means because. We factor it, and then here's the only thing I've done different. Instead of replacing u with e to the x right here, if it's easier, you can set each factor equal to 0 and then substitute in. So notice on this one, once I got to u minus 2 on the problem A, I replaced each u with an e to the x, and then I set it equal to 0. In this example, same thing's happening, I'm just changing the order. I am first setting the factor equal to 0 by solving, and then I'm substituting e to the x. Just a reminder here on this line, and you're going to see me make use of this super convenient shortcut, natural log of e is just 1. Because, and we'll just write it out here in case we need it, recall the natural log of e is the same thing as saying log base e of e. And then we just think, well, this base of e to the power of 1 is what we need to get the argument e. And this is going to keep showing up over and over and over. Super convenient. You might need to remind yourself or consult your factoring checklist, but these things, if you can factor quadratics, piece of cake. Cool. Now, all the examples that we've seen in this section so far have been focused on solving exponential equations. So it makes sense then that we're going to transition to the other side of this coin, where the second main idea in this chapter, and it's going to go quicker, we're going to look at solving exponential, or solving logarithmic equations, I'm sorry. So solving log equations. Now, in solving log equations, there are a few different properties in languages that I'm going to use that I don't think the textbook uses, but I think it's super convenient. As we go through these, 2 ways in which we can solve any of these problems. So they're going to wind up being the same, but it's just whatever one clicks more clearly in your head is what I would suggest you to use. 2 approaches. The first of these is to use the definition of a log. Now, remember that if we have log base b of x, and we claim that it equals some, I don't know, y, the definition of the log says that this expression right here, this equation, can be rewritten as an exponential. It can be changed to b to the power of y equals x. This is the definition of a log. Now, to undo a log, you can use this definition, assuming that you have something equal to it on the other side. Alternatively, which it winds up being the same thing, but alternatively, what I would rather do is use the fact that logs and exponentials are inverses, and I am going to introduce a word here. We're going to say that when Holloway does this, he prefers to exponentiate. To exponentiate. Now, with algebra, remember, as long as we do the same thing to each side of the equation, everything shakes out okay. So when I talk about exponentiating, I want to undo a logarithm. And I can do that using the inverse property, where we're going to raise each side of the equation, using the base. Now, for an example of this, just because this language and it works better just to kind of play around with it for a second, let's dig in and I will show you this exponentiation idea, because this doesn't super make a ton of sense, I would imagine, but when we look at an example, hopefully you'll agree that exponentiation is so much easier. So we're going to work some examples, and I'm actually going to sneak them over here, and I'll remind us of one property here. So example, where all I want to do is solve. And in red, you already have this written down, but I'm going to recall a quick inverse property. If we have a, and let me go here, let's say we have log base 2 of x equals 5. Now, in this situation, the definition of the log seems like it might be easier, but here's what I'm going to identify. If I want to undo a log base 2 of x, I can simply use the exponent, And what I mean by that is if I exponentiate base 2, and I'll write this out, exponentiate base 2. What this means is I could raise the entire left side to the power of the base 2. So we would get 2 to the power of log base 2 of x. But the algebra says that, hey, whatever you do to the left side, you better do to the right. So I would just simply raise the right side to the power of 2 as well. In doing so, we get our inverse log property, which 2 to the power of log base 2 of x, they just undo each other, and we're left with x equals 2 to the 5th. All right, this property, our inverse property, remember, a logarithm undoes an exponential, and the exponential undoes a log. So we get this lovely expression. So here we go, jumping in. I want us to solve a couple, and just like we did before, I'll do the first one together, and then I'll give you a chance to do one on your own as well. So here we are, let's get wild with it. I want to know, when is it true that log base 2, so log base 2, and I hate the way that L looks, but that's okay. Log base 2 of 2x minus 3 is equal to log base 2 of x plus 4. Okay. Now, in this problem, there's several different ways you can think about this. If you want to use the one-to-one property, where I see these are both log base 2, we can just set the arguments equal. So very specifically, if you look in your notes, we see something that says ln x equals ln y if and only if x equals y. We can use that property. It will work for us. However, I want to highlight that in my mind as I'm thinking about it, this might be the property that I use, but just as easily I can do the follows. If I exponentiate both sides of this equation with base 2, because that's the base of our logarithm, my expression looks like this. And it feels clunky for a minute, but despite that clunky feeling, this winds up being super useful when we get into harder problems. Now, by doing this, I see that 2 and log base 2 divide out, and 2 and log base 2 divide out. We are simply left with 2x minus 3 equal to x plus 4. Cool. We have taken what seems like a hard problem and boiled it down into something that's so much more manageable. I'm going to subtract an x from each side and simultaneously add a 3 to each side, and we wind up with x equals 7. And we have it. Okay. Cool. One more type. There's actually a couple more types that I want to look at, but I want to do one more here on the video before I just cut you guys loose, and let's check it out, see if we can't get an ugly one. So here, let's try the following. I want to know if their arguments aren't, if we're not just setting the arguments equal, what are even our possible options. So let's deal with the following. I want to take log base 6 of 3x plus 14. And I'm going to have to slide over a skosh here. Log base 6 of 3x minus 14, or plus 14, I'm sorry, minus log base 6 of 5. And I'm going to claim that this equals 2. All right. Now, this problem is noticeably more challenging. And the thing that makes this noticeably more challenging is that there's not a log on each side. I can't just set the arguments equal. Now, as I look at this side, and as you look at this side, I would imagine that any sort of anxiety that you might possibly have comes from this side. And here's my thought. This would be nicer if it were one log. Because if it were one single log, this would be easy. I wish this were one log. And I'm going to even be more specific. You do not have to jot this down exactly, but If this were a single logarithm on this side, this problem would get so much easier. Now, the fantastic news about this is we can make it that way. If I see the same log base separated via a subtraction, then I know that I can rewrite that as a single log where the arguments were dividing. So let's do that. I'm going to use this lovely green color, and I'm going to condense this logarithm on the left side, or these logarithms, into a single expression. So here we go. This becomes log base 6 of, we have a numerator, which is 3x plus 14, divided by 5. If they're separated by subtraction, then the arguments of a single logarithm would divide, and that's still equal to 2. Now, for this next one, really important that you guys pay attention. I'm going to switch back to red for a second. You can think of the definition. That is not the way that I normally think of the logs. I would rather undo a log base 6 by exponentiating base 6. And instead of realistically writing this over and over like I did on the first one, I could go 6 log base 6 blah blah blah, and I could write the whole thing out. However, remember, mathematicians are lazy, and I'm lazy. So what I would suggest doing is, as long as it's clear, I'm going to exponentiate both sides just as it's written. 6 to this power equals 6 to this power. And I know the equal sign is in the wrong spot. It should be here if we wanted to have this expression look right. But these 6's right here, this is what we're referring to, or I'm referring to, with exponentiation. So this is exponentiate. I'm just going to say expo for exponentiate base 6. And the reason that we do this, and that I do this, is this property is easier for me to think about. 6 to the log base 6 of whatever, they fall out. They undo each other. Those are inverses. Which means, the left side, all that remains is 3x plus 14 divided by 5. Equals, on the right side, I had 6 to the power of 2, and I get a 36. And now we are cooking with gas. I'm going to multiply both sides by 5. So we'll do this by 5 and this by 5, onward to our next step. And let's see, this looks like 168. Ugh. That's not right. That's 180. Is it 180? 5 times 30 is 150, and 5 times 6 is 30. Yeah, that's 180. There we go. I'll now subtract 14 from each side of this equation. So 3x then is equal to 166. And finally, we end up with x is 166 over 3. And it looks like we have it. Cool. Looking at expressions like this, if you can condense it, things get nice. I will always default to using this idea of exponentiation whenever I have the opportunity. Okay. We are about 25 minutes in. I want to look at one more with the understanding that we might have to just do examples tomorrow, but that's all right. I want us to do one more type of example and a single problem. Then you will be trying some examples and some homework problems with your group with lots of questions tomorrow if need be. So here we go. Last example. We're just going to talk about weird solutions. And remember, my shorthand for solution is SOL. I guess it's apostrophe N. Solutions. And let's just check this out. So without getting too completely crazy, let's knock out one of these. I want to know, when is it true that log of x plus the log of x minus 9 is equal to 1? Okay. In this problem, log x plus log of x minus 9 equals 10, or equals 1, I'm sorry. Two things I want to just be really aware of. First off, if we don't write the base of this logarithm, then it's the common log, base 10. We don't have to write it. The second thing is, man, 2 logs on one side kind of sucks. But I have good news. Even though 2 logs on one side is lame and maybe it makes the problem hard, we don't have to keep it that way. We can condense this as follows. And you guys have gotten practice with this. I think this becomes the log of x times x minus 9. And I'm using brackets just to keep it a little bit nicer. And we'll go one more step, log of, and here we go, x squared minus 9x. And all I did was distribute. So I'll make a little note here. This step I've rewritten using the product property. And then here I just distributed. Okay. Once we get here, I'm going to use that fancy exponentiation idea, and I'm going to raise both sides base 10, or exponentiate base 10 to undo this log. So here we go, expo, that's my shorthand for exponentiate, base 10. Now, I will not in this video do the ugly way, the shorthand that I talked about a second ago, but I'll write it out instead. So here we go, 10 to the power of log of x squared minus 9x is exactly equal then to 10 to the power of 1. I've exponentiated both sides of this equation to undo this log, which means one further step, we get x squared minus 9x equals 10. Okay, our primary focus right now is not on factoring, but I'll walk through it. If we're solving this, we want to set this equal to 0. And I'm going to make a note here. Now, solve by factoring. That's our next step here. Solve by factoring. To achieve this, nothing too crazy has to happen. I'm going to subtract 10 from each side. So x squared minus 9x minus 10 is equal to 0. And I see there's a leading coefficient of 1. And I think that I can get this to work with negative 10 and 1. Those are multiplying to be negative 10 and adding up to negative 9. I'm good with that, which means our factors wind up being x minus 10 and x plus 1. Okay, it doesn't seem like maybe anything weird has happened yet. By setting each factor equal to 0, we get x equals 10 and x equals negative 1. Cool. Seems like the same type of problem. Here's the issue though. When we're solving log equations, huge warning right here. We need values of x, specifically in this case, that make the argument greater than 0. We cannot take the logarithm of the argument is 0. Can't happen. Remember, because there's nothing that I can raise a number to, any power that exists that would make it equal to 0 when I do that operation. With that in mind, the important thing that must happen when you're doing these logs is check answers. Now, really important distinction. Really important distinction. I don't have anything against the x values that we get being negative. What we have an issue with is when I plug them in to the original log, if the argument becomes negative in the end, then it doesn't work. So what I mean by this, and you don't have to physically write it out every time, but let's just check. If x is 10, and I look at my original expression, I would have had log of 10 plus log of 10 minus 9 to give me 1 equals 1. Now we can verify this. Log of 10 is 1 plus log of 1 is 0. Hey, that works out. 10 is a good answer. When we check negative 1 and I plug it in, I get the log of negative 1 plus the log of negative 10 is equal to 1 is what it's claiming. However, I didn't even have to write everything. This first term that we write, no. Which means we have identified an extra answer that doesn't make sense. So I'm going to cross out the negative 1, And then just as a reminder, x equals -1 it was an extra answer that didn't make sense. And the formal language we use is extraneous. You must check your logarithms and the values of x to make sure that your argument winds up positive still. So, a little bit longer of a video than I was intending necessarily, but I will have you guys work through some problems using both the exponential and logarithmic equations, and let's take a look. I want you guys to be working through the following problems, and I'll write it down here in the corner. And let's check it out. Your homework, that reminder, I want you to spend like no more than 40 minutes outside of class. I certainly think we'll probably have questions tomorrow. We'll deal with it. But here we go. We're going to call this homework 3.4, which you will find on page 235. Starting there anyway. And I want you to do the following problems. I want you to solve for me. First of all, we're going to knock out the vocab. We're going to say it's 1 through 2. 1 and 2. Weird. And then let's check out 19 through 35. Odd. And then I'm okay with exact solutions rather than approximations, but I also want you to check out 45 through, I lied, 49 through 59 odd. Cool. If you have questions, remember it's okay. Try your best. I would encourage Calc Chat if need be, but let's plan to have this done, hopefully, but at least attempted by tomorrow, which looks like the 19th of November. And I should be back, pending, Zeke recovering and such. But hopefully you found this video helpful, and don't hesitate to reach out. Get started on this assignment. No more than 40 minutes outside of class. All right. Thanks and good luck. Work together. Lots of questions. Have a good day.